Well, thank you very much for the introduction. Yeah, this talk was presented first at SMASH 2015 at the Mnova users meeting, and I was asked if I would like to show this to you as well. So, well, first of all, welcome everybody, and let's get started. Okay. A little bit of an outline. I will give a short introduction into DSM and our department at DSM, and then I will go into the results of the quantifications, and with closing statements, and any questions that you guys have. Oh, first of all, DSM is a life science and material science company. We're trying to improve the world and try to make food products or material products for all kinds of applications and all kinds of brands. Well, actually, the results from this year just came in, and they are quite nice. We play in all sorts of markets. These are several of the markets that we are currently active in. So you can see the material science side, but also the food side and animal feed as well. DSM has innovation platforms in the biomedical industry, the bio-based products and advanced services. Within the DSM bio-based products and services, the DSM Biotechnology Center plays a major role in developing of new ideas into products. The NMR department from the DSM Biotechnology Center, we have three field ranges, the cryoprobe NMRs of 400 MHz, 600 and 700 MHz. We also have two 500 MHz flow NMRs. And of course, 14 people working for us with over 30 years of experience in qNMR. Now, there are several ways how to quantify your components, so let's get into that. First of all, what we do is we add an internal standard to our sample, lyophilize it if necessary, and then dissolve and measure the samples. It is of course important to measure under quantitative conditions. I will not go into that, but typically you want a long relaxation delay, 5 times or more of your T1. And for the rest, there are several pulse programs available, which I will not go into detail. And from the integrals, you can calculate quantifications with this formula, which is posted. You can do that from the integrals and put them in Excel, or use a qNMR or estimate from within Mnova. It is important to note that there is a direct relation between the concentration and the ratio of the internal standard versus the compound integrals. Okay. Well, for these tests, I use validation data sets of 24 replicates of 2 samples of equal concentrations. I will call them sample A and B for time's sake, and a 21 replicate of a 1-to-1 dilution of these both samples. These will be called sample C and D in the presentation. And these were used to measure a combined precision of the measurement and sample preparation, as was done at the NMR lab. Okay, for the processing part, there are several ways to look at your spectra. you can use the pre-processed spectra from, for instance, Topspin, or you can process your data within in Mnova using a processing template, or do it manually or in a series. And you can find on the blogs of Mestrelab how you can do that. And many users, of course, already know this. For the peak integration, there are options. First of all, the GSD was used, and line fitting, as well as integration and peak weight integration. That's introduced, I think, almost 2 years ago now. And I also had a look at that when I did the experiments. Okay, so let's get into the actual results. So what I first did was change the number of fitting cycles for the global spectral deconvolution. You could already see from this relatively easy plot that for the number of fitting cycles that you have, whether it is 1 to 20, you can see there's a difference after 2 fitting cycles, that the differences are almost gone. So basically what the plot says is the relative internal standard height, the relative height of the internal standard compared to the number of fitting cycles. And here you see the spread of the 24 samples, and on this side you see the standard deviation of the 21 samples. You can also nicely see that after 2 fitting cycles, also the outliers are all the same in both areas, so that does not change much. For all these comparisons, there was the same apodization, and phasing was used, as well as baselining, which was a spline baseline. Okay, now the same numbers, only then looking at the glucose concentrations that were calculated using the internal standard. And here you can see also that the deviation that comes from after 1 fitting cycle, and you see that's much more significant, while after 2 fitting cycles the samples show very much the same results. There are several outliers, and you can see over here as well as in this part. I've had a look at the spectra, but I could not really find anything that would suggest to me why this is the case. Okay, the same box plot again of the results of glucose. You can see again the variation of glucose levels with the fitting cycles for sample A, sample B, C, and D. And here you also see that after 2 fitting cycles, basically the results stay the same. So this can vary a little bit on what kind with the kind of apodization function that you use, or other experimental differences, but and these results anyway, it was sufficient to do 2 fitting cycles and not more than that. So here I have a statistical layout, so you can see the relative areas plotted over here in the manual processing, together with relative standard deviation for that sample. And you can see that the differences between manual processing and global spectral deconvolution with 5 cycles, you can see that the relative standard deviation with global spectral deconvolution was much higher than actually was expected. And again, also with a bad or a poor variation in your internal standard, and also the compounds of interest, they will also show a higher deviation, which you can see over here, and the actual values are also quite low when compared to the manual processing. When I first saw these results, we started to ask Mnova about this, why the differences were available, or why we could see such differences. And basically what was said is that the singlets are quite difficult to process with GSD, as there are various line shapes and artifacts that can pop up during processing. So especially strong signets, like the internal standard that we use as maleic acid, it has a strong signal, and it has more effect of this. So I made a plot of the internal standard in overlay of 42 spectra. And you can see on the side, you see the spectra as they are, and on the right side you see the GSD spectra in overlay, and you can see that the line shape of the internal standard is not as pretty as the mathematical function that GSD is giving. So actually the GSD makes two nice functions for the actual results. So we started to look for a different way to do the comparison. Some of you may already have read about this in the blogs from Carlos or Mike, but here there's a short summary of what we did. So first of all, we started to do line fitting. After that, we did a sum integration, and also tested the AddSome integration. I will discuss those in this order. Okay, in this plot you can see again the relative area of the internal standard compared over the 4 samples. And in this part you can see the peak fitting, or the global spectral deconvolution with 5 cycles. You can see the variation in there. And the relative standard deviation was giving results from 2.6% to 7.5%, which was too high for our estimation. So we did a first line fitting with a number of cycles of 150 coarse iterations and then 100 fine iterations. And then we got these results. And the variation was even bigger, and that was not something that I was expecting. So I asked Manuel about it as well, and he said, well, just do more coarse iterations and number of fine iterations. And so after doing that, we could see that these results came up, and relative standard deviation of 1.1 to 1.4% became visible. And this is much more what we were expecting to find. So when comparing these with fitting methods, the manual processing and the line fitting at the second, these show very much comparable results. Statistically, you can not pull these apart. However, if I also looked at the line fitting of the first part, you can actually see that the large variations of up to 10% is actually reduced again when looking at all at the standard deviations that were found. Well, first of all, this came as a big surprise. However, there are also suggestions in literature that this is actually going on. I don't know exactly why there is such variation. It may be due to peak shape deformities or due to shimming differences. But anyway, how many times I tried to reproduce the same results, I could not get this to work, only if I fixed the peak height. And peak height is also something that is known from literature that can be used as a quantification method. We do see that there is a difference in absolute quantity, but the variation is very nice. So let's have a quick look at other integration methods. With the same processing as with the manual processing, I could obtain nice GSD results. There is some bigger variation in the relative standard deviation, but depending on your application, it might be interesting as well. And here also the line fitting gave a little bit less good results as the previous one, but that's probably due to the same processing. But some integration gave actually the same results as one would expect. Now AddSome also gives the same variation and same absolute quantities. And this is also expected, of course, because AddSome, if there is only one peak within the area that you are summing up, then the added sum will assign the entire area to that one main peak. So again, also the results from glucose in this case. When comparing the sum integrations and the AddSome, then you get the same results as you would get with the manual processing. And for the GSD and line fitting, you get higher relative standard deviations, but also higher absolute quantities. Now with the same processing, the different integration methods can be of course compared. And now that the accuracy is good, the trueness becomes more important to have a look at. For that, baseline is absolutely the key. In this picture you can see that the manual processing, you can see the red line that's running underneath everything. That's where the spectrum is baselined in manual processing. With polynomial fitting and spline fitting, I get very comparable results. They are both here in the green color, and adding just one extra data point to the correct spline, I get a much better fitting of the manual processing to get to this result. Okay, so comparing these baseline methods, you can see that the variation is more or less the same in all conditions. However, the absolute quantity, that differs a little bit. Now the results are very close, and to be sure which absolute quantity is the best, you actually need to do spiking experiments and do that in your sample, so you can find out what is the real trueness. These experiments I have not done yet, so we will give you general conclusions. The sum integration is the easiest and most stable way to quantify components, especially when it's a clean spectrum. You can have clear peaks, then sum integration is the best way to go. And baselining methods, they influence your quantitation results, the absolute quantification results quite significantly. So spend time on selecting the best one, and that of course can change from which kind of application that you're using. The variation in peak shapes can be compensated with line fitting, especially with fixing the peak height. You can change, still. And what was most important for us is to see that the automated procedures in Mnova can actually achieve results that are comparable to what is done manually. And this, of course, processing speed up, and the data processing is also more uniform. With those conclusions, I would like to close the presentation. Now let me go to the questions.